Hello and welcome back to the CodeMaven Bootcamp. Hi Nora.
Hi.
My name is Gabor Sabo, and in this episode we are going to do something else, not talk about Python. And actually, what we are going to talk. So we get back. Okay, I'm sharing the slides now, right now. Okay, and on the CodeMaven website, you might remember the beginning we talked about that there's a slash slides, which where you can find the Python programming slides. But here too, also there is somewhere programming intro. This is the title, and we are going to go over that because I put it separately. This is a little bit more generic thing, and we actually covered some of the parts here already in previous videos, and they are mentioned. In the main list uh, uh, of the programming bootcamp, where you can see each part where it's mentioned. So as we go over, we'll probably skip some of the slides because we have already discussed it earlier. But we're talking a little bit generic information about programming and a little bit about what is in a computer. So um, in some of the classes actually that I gave, some people came to me and asked me, okay, so what kind of computer I would suggest them to buy, and that was a good opportunity also to talk a little bit about what is in a computer, so to have some generic background. I'm not really much details, but some generic background, and especially the parts that might be relevant for someone writing programs, okay, and when would like to buy a new computer, okay. So this one, basically we had some similar slide in the beginning of the Python course where we discussed that there are various types of applications that you can write software, and I don't know if you have, they're like embedded applications like what you have probably on a space shuttle or in a car or a fridge or in a pacemaker. So these are what we call some of these are what we call embedded applications, and you wouldn't write them in Python, for example. They usually need to be really small, really fast, um, and you don't need, and it's worth the investment of other languages, usually C or some even some specific language, to make it right for these kind of applications. Okay, and then we talked about the CLI interface, the command line or the command line applications, and mobile applications also. So theoretically you can, or actually not just theoretically, you can run Python on your mobile phone. But basically there are two types of mobile phones, right? The Android phones, or phones that run Android operating system, which is, by the way, beneath Android, that's actually Linux. So it's covered with some UI, which is called Android, but beneath that it's actually Linux. And the other one is the operating system of Mac, which is the iOS. I think that is the name of the mobile operating system. And in both of them have their own language, or actually some of them have several languages. For example, for Android, you would write in Java, or there's another language called Kotlin, which is specific to that, but it's very similar to Java, basically. And you could write in Python, but for Python, for example, you don't have access to the UI of the mobile phone. So you can do, I wrote a long time ago, actually, a little application. It was in Perl, but it doesn't really matter. Python would do the same. That could log the coordinates that you have from the GPS signal. So that's just like all of the programs that you can track your how you run and where you hike and all these things. So that was like, I don't know, three or five lines of Python code, just getting the recording part. Of course, it didn't have a UI, nothing like that, but the recording part was really simple. So things like that you could do, but you can't do it with Python, really, applications for mobile. Web applications, so in a web application, you have the one that comes to in your browser, right? The HTML, and it's the HTML that we actually saw, I think, when we talked a little bit. So what you would get if you click on view source. And then there is another language called CSS, which is for the styling of it. It's called cascading style sheet, which is for the styling of the colors and the location of the things on the UI. And there is a programming language which is called JavaScript that actually does all the actions in your browser. So this page is very static. It has nothing, there's nothing, just clicks on something. Actually, if I click here on the question mark, you can see this pop-up window that says what keys can you use, and this the acceptance of these keys, the specific keys, is actually written in JavaScript. So that gives us some interaction with this web page. But for example, in an application like Gmail, which is a very common one, a lot of things is written in JavaScript that do all what's moving around. But all of these are talking to some program on the server of the company. Okay, so for example, on the server of Google, if that's Gmail. And that part can be actually written in Python, because the front end is only these language, only these things. You can't use any programming language, other programming language besides JavaScript, basically. On the back end, okay, and also this is also usually called the front end. On the back end, which runs on the server, you can use any language, and many times they use Python. Okay, so that's just a place where you can, and it's actually quite easy to create your own web application. And that was, I remember that was one of the first things I wrote in a company where, as an in-house web application. So we had some machine, and I wanted to offer the services of that machine to the other people in the company, but I didn't want to give them access to the machine, full access, because they would do all kind of nasty things to the computer. They would copy files there in an incorrect way and so on. And so I wrote them a little web application that gave them the access exactly to the features that they needed. Okay, and this can be actually done. So you don't need to create a web application to go out to build a website to the public. It might be inside your lab that instead of building a GUI application with TK that runs on their own computer, maybe you create a web application that runs on your computer or some central computer in the lab and gives services to people. For example, you can use that application to run a machine, that control a machine that you use, or fetch data from something. So and then you build this web application. And that's not that hard with Python, okay? We can, at one point, we might have actually a video about that separately, probably from the bootcamp, but that can be an interesting thing, okay? Okay, so now let's talk about a little bit about computers. So this is just a list of stuff that's in the computer, okay? With all kind of links to Wikipedia mostly. So let me just, let's just look at if they have pictures. Well, this is a very blurry one. Okay, computer hardware. Okay, you can't see really much here. Just remember that the first computers were huge, like your room size, and now they are so tiny that we can't see them. Okay, but what is in the computer? So the computer basically is a lot of hardware. Okay, the iron that we have, and we have the software that we were talking about earlier. And the main, so there are several parts of this computer. I thought about saying main, but it's not really the main. It's just the central processing unit, which does all the computation. Okay, and if you, this is called the CPU. So when you buy a computer, or when you talk about a computer, you usually talk about the speed of the computer, the speed of the clock in the computer, and sometimes these days we talk about how many cores a computer have. Okay, so in the older days there was only a single CPU in the computer, and it had one core. So basically it could do only one thing at a time. And then in order to allow you to have multiple windows open, the operating system was just switching between them all the time. giving each one of them a little time. And because it was doing it so fast, the switching, that you didn't notice usually, that it gives the feeling that they are running at the same time, while you actually do only one thing at a time. Okay, these days, okay, and then later on, some computers got many CPUs, but they were really expensive, or usually very expensive. These days, they found out that they can put on the same CPU, on the same board, multiple CPUs basically, but we just say that they are cores. So instead of having, let me check if there is a good image for it. I think it has. So a CPU, it looks like something like this, with lots of flags on the other side, and it generates a lot of heat. Okay, that's another thing that it does while it's working. So in this such a, yeah, okay. In such a CPU, you might have multiple of these processing units. So if you have 4 cores, it means that you can actually, your computer can actually do 4 instructions at the same time, really at the same time. Okay, so not just pretending to be. So it usually it's better, the more cores you have, the better. But the programs that we wrote so far, they were straightforward, using only a single core all the time. So that for our programs, it didn't matter that we had multiple cores, because they were only using one. Where it matters is that that you have multiple cores, that maybe the operating system runs on one of them, and your program now free to use a full core on its own. Okay, or later on you might learn how to write multiprocessing programs that run on multiple cores, which is a little extra work, because you have to think now, okay, what things can I actually compute in parallel? Because so far we're thinking, okay, do this and then do this, and then we always relied on the data we got earlier. But there are some things that we can do actually in parallel, but we have to be more careful with this. But that's the issue of cores. And the clock speed is how fast basically these instructions are executed. So usually you want faster. But there's a third parameter basically, or big parameters, is what we call the instruction set. And usually what we see is just a number. So an old computer, which is a 386 or a 486 or a Pentium something, or these days they are usually called i3 and i5 and i7, all these numbers, all these names basically. And what they cover is basically what kind of instructions each CPU has. So in Python, we had these instructions of len, the functions basically, okay, or the plus operators. All these are statements or operators. These are the words we use. In a CPU, they call instructions. So each instruction, you might remember that we had this exercise about the assembler. Okay, so those are basically the instructions. Move some piece of data from one place to the other, add together. And originally there was a small set of instructions, and they added more and more interesting instructions. And one of the key things that they added is actually, later on we are going to talk about when we're talking about the FPU. Okay, so for example, at one point, they added a set of instructions to be able to calculate floating point numbers. Earlier, they could calculate floating point numbers, but they had to they thought about them as individual digits. And now they have specifically designed tools to compute the floating point. And why is it interesting? And let's jump now to this floating point unit. So back in the old, at one point, they understood that, okay, we need to speed up the calculation of floating point numbers. So they created a separate unit that would be able to do that fast. And then later on, they integrated into these sets. And so that's important if you're doing floating point calculations, okay? And we do a lot in some computation at least. So this is what's covered in this. to tell you the truth, I hardly look at the actual instruction set. Okay, so I more generally, I know that probably i7 is better than i5, even though it's not really true always, because they have different sub numbers and sub things. But for us, okay, like at this level, the newer is the better in general. Okay, it's more interesting if you're starting to buy lots of computers, and then you will get into these details. Okay, so way too much about CPUs, but we covered it. So the FPU was separate, and now it's basically part of it. RAM, or random access memory, this is what we call the memory, usually the computer. But these days, many people call both this and the hard disk as memory, especially with the mobile phones. The mobile phone sellers, they were using the word memory for both, or they were primarily using it for the hard disk part, actually. Okay, but if you are talking about random access memory in phones, you usually have a few gigabytes of them. In computers, you have, I mean, I don't think that you can buy any computer with less than 4 these days, but you can easily buy something with 16, and servers can go up to hundreds of these gigabytes of memory. The amount of memory is important because this is what is available fast for the CPU to do the calculations. Okay, whatever is in the RAM is only available while the computer is running. Okay, it's also important to remember. You also have the hard disk, or it's either a spinning disk physically, or maybe an SSD, a solid state drive. It's basically the same that you have on the disk on key, more or less. Okay, but just you can also have it inside a computer. So, and these are disks that if you saved something there, it's there, even if you turn off the computer. Okay, and it's usually doesn't get lost. Okay, I mean, these are still have errors, and they have malfunctions, and so they sort of lose here and there data, but it's quite rare. So here again, phones usually have these 16 or 32 or 64 gigabyte of these. A computer usually have 1, 2, or 3 terabytes of this already. Okay, so a terabyte is 1024 or 1000 gigabyte. Okay, but nowadays, many times computers come with an SSD instead of a spinning disk, and the SSDs are much smaller. So the spinning disks are usually 1, 2, or 3 terabyte size. The SSD in a computer comes with 128 or 256 or 500. That's already quite big. The reason they are much smaller is because they are way more expensive. So you wouldn't be able to afford such a 1, 2, 3 terabyte at this price. I was just looking at, actually, I think, and it's for these external SSDs, and for 512 gigabyte, I think it's about $100, $200. I think it was between 100 and 300. It's also depending on the speed. And I guess for $100, you could easily get a 3 terabyte spinning disk. But the spinning disks are slower than the SSD, or let's be positive, SSDs are much faster, okay? And they are, because they don't have moving parts, you also have a lot, especially in mobile phones, you don't have them, but so in mobile phones, you only have SSDs, okay? You don't have spinnings. But notebooks, you used to have these spinning disks, but it's better to have SSDs usually because you move your notebook a lot, and then it can ruin the spinning disk much more often than with an SSD. Okay, but they are more expensive. Anyway, that's about the disk. So when you okay, and then there's something called the motherboard, which is just let me see if there is a. So it looks something like this. Basically, you put everything on it. So there is a slot for the CPU, there is slot for the RAM, actually the disk, so I guess this SSD would be on it, But if it's a spinning disk, that would be separate. There is something called the bus, which is just like a public bus. Okay, the goal of this bus is just to connect. So this is wire connecting all the other parts, all the parts together. So this is the motherboard, the bus that I mentioned. Then there's on each of these computers, you have what we call a cache. So I mentioned cache at one point a little bit, but let me just talk about a little bit more about it. So the idea of a cache is that you temporarily save something, a result, to make it faster, to make the whole operation faster. It can be from the web, but it's also inside a computer. So in order for the CPU to work, it needs to get the data. If it's on the disk, on a spinning disk, then all the way from the spinning disk, it's very slow. If it's on an SSD, it's already faster. If it's in the RAM, it's way more faster. It's about, I don't know, 100 times faster than from a disk. But even that is not fast enough for the CPU. So they created these small units of memory, basically just more memory, just we are calling them cache. Okay, and we call them L1, L2, L3, which is the distance from the CPU. So one of them is on the CPU, one of them is slightly away of it, and is even further away. And the further away it is, the slower it's going to be, but it's also way cheaper. So that's the trade-off, basically. And so when you think about a computer, probably you won't look into it too much, but if you do, then so just you have this understanding that usually the more of this cache, the faster it's going to be. So it's sometimes not worth much to get a really fast CPU if you don't have a cache, because it won't get the data enough fast enough. Okay, so these things have trade-offs. And if we are already talking about the trade-offs, one huge thing, and that was the big question of that person who was asking me what computer to buy, is that he said that he has a budget and he wants to decide whether to buy a fast. So the big question was faster CPU or more RAM. Okay, that's usually the big question. I mean, there are all kind of other things like screen size and other things, but internally, for the speed of the computer, these are the two big parts. And I usually recommend to buy more RAM, because in most of the computers I saw, the ready-made computers, especially desktop, maybe less so in notebooks, they were getting very fast CPUs with too little RAM. And the CPU couldn't really use, you couldn't really use the whole CPU because you didn't have enough RAM to feed it. So that's my feeling. Do you have any questions here?
No.
No, okay. So you also have all these things of input devices that we know, and output devices like a screen and a printer. And there is something called the BIOS, which is the first thing that starts running on the computer. So usually when you turn on your computer, you see some text thing, and maybe you see that press delete or press F2 to get into the configuration. And there you can configure things like in which order the computer should check the hard disks or the disks when it boots. So you might have a CD-ROM and the hard disk, and the computer can boot from the CD-ROM. But you have to configure in the BIOS to make it check first the CD-ROM, not go right directly. And you can also configure to check the USB drive. So you can boot a computer from a USB drive. But you might need to tell it in the BIOS that you do it, that the computer will check it. And these are very low-level configurations of the computer. Okay, connectors. Okay, so the computer has all kinds of connectors. PS2 is the really old for the mouse and the keyboard. You can have all kind of, I won't go into details here, all kind of video connectors. These are just how they get, I don't know if, I'm not even sure, I think HDMI is newer than DisplayPort, but there are various things. Then the USBs. There's something called RJ45, or also called Ethernet. That's where you connect the network cable if you have that kind of connection in your computer. For example, I think for example, I don't have it anymore, but then you can use this USB to Ethernet connector if you would like to connect, and then you can use through from USB. I also have tons of these connectors between these. So for example, I have my computer has an HDMI connection, but my screen is old and it uses DVI. So I had to buy a connector, and I have tons of these. And well, there is the wireless that we know, Wi-Fi, that is a relatively short range. So it's a couple of tens of meters usually. And then there's Bluetooth, that's a couple of meters. And these are both for connecting basically devices. And then the audio cables and whatever. The phone cable is something else. It's called RJ11. That's a regular phone. I'm not even sure in other countries, in which country it is used. Different countries use different plugs for phone as well. So. And then there were other connectors like called Firewire and Thunderbolt. I think Thunderbolt is for Macs. I'm not remember. These are just all kind of connectors which you can find on the computer. We talked about bits, right? Okay, so 1 bit is based, because of the transistor, is 0 and 1, and then 1 byte was 8-bit, and so on. And because of this, we are using the 2 base, because how the transistors work. We discussed the year 2000 problem. So
yes.
Yeah, so I won't go into it now. If you are watching the video and you're interested, then find it out. Find the location of this in the table of contents, basically on the main page of the programming bootcamps, and then you can find in which video and at which minute we were talking about it. And the 2038 problem, right?
Yeah, same.
We also saw that incorrect floating point problem. These are generic problems with computations. This is just an example in Python, but in general, other programming languages have similar issues because it's the underlying how we store data. And there are solutions for this, but usually we don't need them because the errors are too small. Operating systems. So you're using Windows right now. I also using Windows, but usually I use Linux. And there is also Mac OS, which is or OS 10, the names usually, that runs on Apple computers. And people usually call that they either have a PC or a Mac. So Macs run this operating system. A PC would be able to run either Windows or Linux. Okay. That's just personal computer. That's the PC, where PC comes from. And then Unix, which were various versions of Unix. These days, they are much less used because almost every place Linux replaced them. And there are lots of others. Okay, so there are many other operating systems for either desktop or servers. Oh, and just to clarify, a server is just another computer that usually doesn't have a screen. Okay. And usually they come in like a pizza box. Okay, that's how we call it. So they are really, really flat, and they're huge, and they exactly look like a pizza box. So this is how we call them, pizza box. And the reason they look like is because you put them in a rack, and then you can have hundreds of them, and one after the other, one above the other. Okay. They are designed especially to put in such places. Okay, and then on mobile systems, you have the iOS for Apple and Android, which is Linux based. But I mean, almost all the, but yeah, so the iOS is only used on the hardware of Apple, and Android can be used on all the other mobile providers. And then there's also something called Windows Mobile that from Microsoft, but it was discontinued several years ago. And probably there are others, very smaller ones that very few people know about them and use them. And then there are a couple of other operating systems for embedded systems. Okay, right? Remember, for example, the VxWorks is an operating system specifically for embedded systems. Okay, and there are all kind of others, flavors of something and so on. So I'm talking about a little bit about this, so you have this understanding that like it's not just Microsoft Windows, as most people would think, and it's not even just Linux and Mac, but there are lots of other things that that are used in our world. I don't even think that I have a slide for IoT. So IoT is what is called the Internet of Device. IoT, Internet of Tools, I don't remember. The idea here is that basically every thing in the world can have some computational power, and then you can Internet of Things, yes. So, and then you can connect them together in the internet, and then they can talk to each other, and then it can be something low level, relatively low level, like your fridge that maybe even knows what food you have inside, so you can talk to, some application can talk to it, or the autonomous cars that can talk to the street lights, and they can talk to the other cars and to the street, and then they don't have to keep distance, for example, like we do, because they talk to each other. So if the first presses the brake, then it can also tell the second one, so you don't have the waiting time. So that's a whole separate world, which is huge. The programming paradigms, okay? And did we? No, we didn't talk about this, right? So
no, we didn't.
Yeah. So there are a couple of these styles of programming, or the official name is programming paradigms, and I don't have a link there, but don't worry. Some partially this is how the world evolved, and newer paradigms were created, but usually the olders weren't abandoned, and we're still using them, and sometimes we're using intermixed. So there is what originally was what's called imperative, where everything was like without functions. Just think about it. You write code without functions. Okay, just do things, do this. So you don't write functions. The language might have functions, but you don't. Okay. Then there's a procedural, or that's part of sort of the imperative, which is languages like C and Bash, where you have already functions, but you don't have objects that has attributes and so on. So languages like, and in Python, you can program this way as well. And then there is object-oriented languages like Java and C# and C++. You can't write anything without creating a class for it. And we have spent, I don't know, already 30 hours or 40 hours learning about Python, and we haven't created a class yet. We use classes, we use the attributes, like these are all classes and objects from the classes. So we use that, but we didn't need to touch them. If we were creating more complex systems, okay, or in the advanced part of the Python course, usually I teach about how to write classes, okay, and how to create. So in Python, you can also do this, but in other languages, you can only do this. So you can't have a program that only functions or only statements, okay? Then there are languages which are declarative. So there's a language, especially the most well-known is SQL, which is stands for Standard Query Language. Do you know about databases?
Not from this point of view.
Okay, so there are couple of styles of databases. The one that the most well-known are what we call relational databases, okay, which are basically tables. Think about them as Excel files, basically, that are somehow interconnected. So I know, for example, I have a list of people, and then I have a list of courses, let's say the university, and then I have somehow I know that which person studies which course, and these are three tables basically somehow connected. Okay, and in order to talk to these databases, we have the language which is called SQL, the standard query language. Now in the SQL, you don't say if some, you don't say, well, you don't say things like do this and do this and do this and do this. You say, get me this kind of information where these conditions exist. And the engine behind it figures out how to do it. Okay, which order to go over the data, how to filter the data, and all these things the engine decides. So this is why it's called declarative, because you don't tell the computer how to do things, you just tell him what the result you would want. Okay, then there is also functional yeah, in Python you can't really use SQL or sorry declarative style really, but I'm sure that there is some extension that you can play with it. And of course you can use Python to access these databases and send them over their queries. Functional, it's just a type of declarative. It's a type of declarative. Languages like Haskell are purely functional. Okay, they are also on the website of Haskell. It says that runs on PhD, because you really need to know a lot in order to be able to program in Haskell. I think that Haskell is one of the languages where the easy things, where difficult things are easy, and easy things are difficult. Which, if you now have to handle those difficult things, then it might worse the investment. But if you do relatively easy things, I'm saying easy comparatively in the programming. What we do is like in the programming world is relatively easy, like opening a file, reading some data. That's relatively easy in this. Okay, and these are the functional programs. Now in Python you can also write functional programming partially, and we saw a little bit when we used the map, for example. At one point you use the map function. It is all the advanced part of the course, but we saw a little here and there. Okay, so you can mix. This is the reason that Python is called multi-paradigm. Okay, because also Perl and Python and a couple of other languages, because you can have several ways of writing code. Logic, or it's also a declarative style. For example, Prolog. Now in Prolog, you basically write mathematical equations and then tell it, okay, now figure it out. Okay, and okay, it's very simplification of what I just said. And I remember I studied Prolog when I was at the university, and I loved it. But I mean, almost no one used it in outside of the academic world. And then there are mathematical declarative languages like Fortran, and all kind of others. So there are, I think, like 4 huge paradigms, and then there are sub paradigms in this. And it's interesting, I think, again, for the background, not for the specific use right now. And then, okay, so let's talk about object-oriented for a minute or two. So in Python, everything is an object, right? We can ask the attributes of a string. Even a string is an object. In Java, no. In Java, individual values are not objects. But Java is considered an object-oriented language because anything you write must be in a class. Okay, so when we say object-oriented, the meaning might be totally different. Okay, so in Python you would print something, you know, this hello world like this. In Java, in order to print hello world, you need all these lines. You need to understand what is a class, what is public, what is static, void, and lots of things, okay? And on the other hand, as I said, Python is way more object-oriented in a way. So it's not like less object-oriented, more object-oriented. It's different. Okay, we talked about compiled and interpreted. I think we talked about this. So it's just a
Yeah, we
couple
did.
of this, yeah, a couple of these languages. Open source, we talked a little bit about it, I think.
Just mentioned it.
Okay, so in general, when you write in a language like C, then you write your source code, just as you would do in Python. Then you compile it and you give it to some other people, and they don't need the C compiler or your source code in order to run your program. Okay, so if you go now and buy some program and download from somewhere and download it, what you get is just that executable. You don't get the original source code. Okay, which means, and to get back from the executable, the original source code, it's called decompilation, but it's usually really, really hard to get something working, okay, or understandable, because they don't know what are the variables. So they will just create x1, x2, x1, x2, x3 for all the variables, because they don't know what the variable names were. So it's going to be really, really hard to deal with that, even if they manage to do that. But beyond that, when you bought some program, you don't have the right, you didn't get the license to change the program. So even if technically you could go back, and you don't have the right to do that, okay? And that's really good for the company selling you the software, because now you are dependent on the company buying the newer version, or paying them for support and all of these things. Then like 30 years ago came a movement, about 30 years ago, which was the free software movement. The idea is to create software where you have several of these freedoms, okay? We don't go into that, but there are several of these freedoms. That one of them is that when you get a program, you will be able to change it, to modify it, to use it and modify it and distribute it. Basically, I think these are the three freedoms. Okay, so when you get a program, not only you get the executable code, but you also get the source code and the license to change it and redistribute it. And then that's the free software. And then open source was a movement trying to make it more business-like. So I mean, business don't like the word free. So, and to clarify, because in English the free both means free as in free beer, as in and both as free as in free speech. Okay, and here they are talking about free speech, not as free beer. Okay, even though at the end it's usually also free in terms of free beer. Okay, so that's the free movement. Open source is quite similar, except that those licenses are more business friendly. So in the free software movement, you would say that you got some code. If now you take it and modify it and you redistribute it, the only way for you to redistribute is under the same license. So you can't close it. And this was not very business friendly, because the companies like to grab something and have their own, even if they didn't pay for it. So the open source allowed this. So there are all kinds of these open source licenses that say, okay, here is the source code. You can do with it whatever you like, including closing it and distributing it as closed source software, okay, as proprietary software. And so these days, we are mostly talking about open source. Free software is sort of a little bit more on the fringe, but free software is the ideology behind, really, and the open source is more the day-to-day, or the what is the word? The opportunistic thing. It's huge, okay? Almost everything these days, for almost everything, you have open source software, and it's especially good about Okay, and in Python, okay, I was just thinking what else I wanted to say. So for example, Python itself open source. So you can download the source code of Python, read it, learn about it, fix a problem, and redistribute Python. But you also can, all the modules that you have, you can do the same. And compare it to MATLAB, you are totally dependent on the company. If you find a bug in NumPy, okay, you have the rights and you can learn the capabilities of fixing it. Okay, so okay, so it's so who writes it and why does it matter even? One of the things that I remember was that when there was a long time ago, there was an editor before Windows, before Microsoft supported languages beyond English. Okay, there were all kind of editors for specific languages. For example, for Hebrew, there were editors. They were all proprietary, and people wrote their PhD in that. But then that company went bankrupt, and they didn't give away the source code. So those people have their printed out version of their PhD. Okay, they have a file maybe, but they can't open it anymore because those programs don't run anymore on new modern operating systems. Okay, so they can't do it as anything. If they were open source, okay, they could someone could pick up and fix the code and then at least extract the file, extract the content from the files, and make it easy. Okay, and it can be something like a PhD, or it can be all kind of other things that suddenly are logged in because of this. Okay, so this can matter. So this is, I mean, for me, the freedom matters a lot, that I can really do whatever. The cost also matters, that I don't have to pay tons of, I mean, the license of MATLAB is, I think, a couple of $1,000s a year. Okay, the license of Python is $0. If you add NumPy, it's even, then it's 2 zeros. And that, okay, let's not get there. Okay, so so it's okay. It's not totally zero because if you need help, then you need to rely on yourself a little bit more or a lot more. While in the other case, you just bought it and that's it. But on the other hand, everyone can support it. And if you go to Stack Overflow these days, you see that, I don't know, millions of people helping just for fun. Okay, it's partially for fun, partially to show that they know and that's good feeling for themselves, and partially some people actually display their score, their Stack Overflow score, and using that to justify why you would need to hire them. So people do this, and you get a lot of free help from people. And so I mentioned the licenses. So there is this range that I said. There's a GPL, which is contagious. So if you use that, then everything that you used must be under GPL. So that's and the other one is the BSD, sort of the other edge, which says, okay, you used it, and then you can redistribute it even as proprietary source code. And then there is this sort of fight between these two camps, because they both say that they are more free in freedom. They provide more freedom. So on one hand, they say, the BSD style people say that we give every freedom, even to close the source code. And the GPS people say, in order to maintain freedom for the world, we have to enforce that the freedom is not taken away by someone in the middle. Okay, and then it's the same discussion in all kind of other places, not just in software, but in software, that's the discussion. And then there is this open source initiative, which is an organization that decides which license can fall under this criteria of open source licenses. Okay, and okay, so why do people create open source software? It's because fun. It's a creative work. You can show off. Many times it started that people starting to write some software the old idea of cataloging your CDs, or I don't know, whatever, your sequences, let's say. And then because you don't need it, you don't, you wrote it because you needed it, but you don't want to make money of it. So you can just give it away. You won't have less because you give it away. And actually you're going to get more because people will give you feedback, and people might fix bugs that you haven't encountered yet, but they already did, and then they fix it even before you encounter. And they will write test cases, and I have no idea what. And well, this is at least in theory. In practice, many times they were just asking for help from you. But yes, so successful projects give a lot of value back to the original authors as well. Okay, and what you see in the PyPI is that there are 260,000 of these packages, many of them huge, like NumPy is not a little thing, okay, or pandas that we are going to talk about once. Then there are all kind of, so these are like sort of the individual things. And then companies do create open source and give it away as open source because that allows them to build a user base, and then they can sell services for that on top of that. Okay, they might give you an improved version of their software if you pay money, or various models exist. And then there are others who are just distributing open source or creating open source because they themselves don't make money from software. They might make money from providing a search engine and showing advertisement there. And but their competitors, they make money out of selling software. So now if you can encourage other people and if you can distribute software free, then you basically undermine the competition because they can make less money. Okay, so there are these ideas of why to give away something free, basically. Okay, yeah. So there are languages which we call open source languages, but basically these days most of the programming languages are open source. So you can actually get the compiler, interpreter, the source code of it under a license which is open source. Yeah, basically that. And then you can have these questions whether you have IDs with tools for it as open source or not. That's a separate question. Version control. So we're going to talk a lot about version control later on, specifically about Git. But let me give you a little overview. Why use version control? It's basically, I mean, maybe we talked a little bit about it. It's for fearless, a couple of goals. One of them is the fearless experimentation. Okay, so if you make some changes to your code, okay, you might be afraid that, okay, how do I get back if I made some incorrect change? So what you do is to create a copy of the file, right, somewhere. Okay, and then you go ahead and then you think, okay, now it's quite good, but now I'm going to make more changes. So you create another copy of the file. So basically you're doing version control manually. Okay, so you know why you need version control. You just use it manually. Okay, so a version control system is there to make this easy. And not only that, it also, so it's fearless experimentation, so I can go back anytime I want easily. I can remove old and bad code, or old code, again, fearlessly, because I can go back to an earlier version where the code still existed. Okay, so it's not that I really did it. And I mean, see many people keep old code commented out, sometimes not even commented out in their code base, because maybe at some point we'll need it. And no, you can get the history of your changes. So maybe you know that some feature worked, and then you made changes, and now at one point you notice that feature doesn't work. And you remember that like 2 months ago I was using it, and since then I haven't used it at that feature, so I don't really know when it broke. Okay, And with version control, if you have all these changes, you can easily get back to any point in history and check, okay, was it working there still? And then you can find easily the change that broke it. And then it's much easier to fix it. And to understand why did you make that change? You probably made that change because you wanted some other feature to work. So you don't want to now fix this one and then break the other one, right? And not finally, but this is in the middle, that easier or smoother collaboration. So especially if you have so think about it, you probably have, I don't know, signed an agreement where you, with someone who you had a Word file, and then they sent you over the agreement, and you read it and made some changes, and then you sent it back, and then they made some changes, and they sent you back, and so back and forth. But what would happen if both you and the other person made the changes at the same time in a Word document? You won't be able to merge them together. Okay, so if these days, if you work on Google Docs, okay, it already provides you a single place where you can improve that. But with other things, you can't do this. Okay, so a version control can provide you this easy collaboration in source code, because it can easily merge parts of codes. I mean, as long as you were editing in different files or different parts of the same file. I mean, if you were editing the same line, well, then you still have to figure out how to fix this. But otherwise, the version control system just helps you merge things together. And there are a couple of these version control systems: Git, Mercurial, Subversion, CVS, RSS. I'm going backwards in history here. These days, Git is the de facto standard, especially for open source, and it itself open source. Okay. Software testing, we had a little short section about software testing. So the main goal of software testing is to check whether the software is still working, that earlier worked is still working. And it allows us, again, to fear less changes, because I remember I went into some project with a couple of thousands of lines of code, and I wanted to make some change, and I made the change, and I knew that I ran the tests, and it told me where it's broken now, and I fixed those parts, and I ran the tests, and now they were working. And I knew that the tests were covering almost like 99% of the program. So there is a very little chance that I broke anything, because the test checked that everything that worked before is working after my change. And I had to add a test that was checking my change, actually, the new feature. But I can really easily go into a source code that I didn't know anything. I didn't have to fear of breaking something. Yeah, this is and the fearless upgrade, that's another thing. People are really, really afraid of upgrading things, because maybe the new version is working differently, breaking something. So when you install a module, pip install something, okay, you got the latest. And then 3 months from now, you run pip install again, you will get a newer version that works differently. Hopefully, it will be backward compatible, but how can you know? Maybe you use the feature that they decided to remove because it was such an obscure feature no one really used, but you found it and you used it because that was exactly what you needed. Okay, you were the only person using it. So now how can you easily make sure that everything still works? Well, if you have your tests, then you can run them and you can easily find the issue, find that it works or not. Okay, we talked about ASCII and Unicode. We talked about complexity of how many operations based on the length of the input.
Yeah.
Okay. We talked about the internet. What is the internet?
Not much.
Not much. Okay. So basically, it's a lot of computers. Some of them are called servers because they don't have screens, but basically these are computers. connected to each other using what we call routers. So you have at home a router that can, so you have a cable, okay, so without internet, you would have a cable, and on that cable, you would have computers connected to it, just a single cable. They could talk to each other. But because these cables can only handle some certain distance, okay, we put different cables between different cables, okay, there are long distance type and short distance type data transfer. And in order to transfer the data between them, we have these routers. Think about this as a road, okay? And then you have these places where several roads meet, and then intersections or roundabouts also, doesn't matter, okay? But places where several roads, okay, let's call them intersections, okay? And then there is something that can, well, on the roads, you have signs that point you which direction to go, okay? And these routers basically also have a map saying, okay, which direction should go a request, okay? And each computer has an address, which is called an IP address. And then, but we don't want to remember these IP addresses because they are long numbers. So instead of that, we remember names. So for example, if you type in code-maven.com, your computer translates it with some services into the number where this website is served. And then to the IP address of that. And then using that address, it connects to that. How does it connect? It basically sends some data, what we call packets, okay? It sends some data over the wire, and these routers give you the direction how to get to the other server, okay? So you have these points. Of course, sometimes these things are not connected with wire, but without wire, and that we call wireless. But basically, the idea behind is the same. So your computer, which you might call it a mobile phone, but it's still a computer, okay? Or you might call it, what else do we have? Your what is it called? Roomba, right? The London's cleaning the
no, yeah, it's called Roomba.
Roomba, okay.
The robot vacuum.
Yeah. So it also has some computer inside, and it can talk wireless. So it's just another node in this network, okay? And so on. And then we have these what we call client-server applications. So there are two pieces of this. One that talks to the other. These two pieces of applications. Yeah. And then I think that's sort of more or less enough about the internet. I know it's not really deep. There are various what we call protocols on how the computers talk to each other. And each protocol is for various services. So for example, there is a service called DNS, which is domain name service, okay? That translates these names like codemaven.com to the number. And there are other services like the email, SMTP, for example, is the name of the service that is basically behind the scenes sending the emails. Okay, and they all send these packets, so basically little files, think about little files sending over the internet. And then we talked about a little bit about cloud. So cloud is, it's like a huge buzzword for me, but basically the cloud is just a bunch of computer owned by some other people, okay, that lets you either rent a computer or rent a service on that computer. Like Gmail is the cloud service for email, okay? You might, in some other place, you might have Outlook, okay? It's just the same idea, just instead of having on your computer, it's on some other place, in this case, Google's computer, okay? And then they call it, it's in the cloud, okay? Yeah. Yeah, okay, this is the last slide. So there are these methods of software development. Um, um, they are not exactly the same level of explanation, but for many years and still today, most programming is done in, I mean, not the style that you're going to do, probably, at least for now, because what you do is you have some problem, you think about the problem, start solving it, basically. But in these companies, what they said that, oh, we need to first understand everything that the client needs. And they spent months on it. And then they wrote a specification, again, month of it. And then wrote the coding, and then the QA. And so these things were like a waterfall. That's why they later on, this was named the waterfall style of program development. And it basically doesn't work, but people still use it. And the reason it doesn't work is, especially today, and in most cases, okay, in some cases it might work, but in most cases it can't work because most of us don't really know what we want, okay? And even if we know what we want, in 2 weeks it will change. And by itself, because the world changes, okay? And even if that doesn't change, once I see the solution that you did based on what I told you, I will say, no, this is not what I wanted. I mean, you might understood exactly what I said, but now I need something else. Not because the world changed, but because this is not really. So this idea of that upfront, we know everything, and 3 years later we get something that's what we wanted, it's totally false in almost every case. Okay, so instead of that, there is that's also like at least 20 years old, the agile style of development, where basically the idea is that to work in very short cycles and always get feedback from the customer, whoever the customer is. So in case if you're writing for yourself, then you're checking it's working for you. If the customer is some other lab, then they are the customers, even if they don't pay you, but that's still sort of the mindset, okay? So to get all the time feedback from the customer to see if that's what they want, and then they change the direction all the time according to the feedback and what we think that needs to be done, okay? And then there are all these, and then there's something which is called Scrum, which is sort of a definition of how to make software. They sort of try to equate it. Scrum is basically, well, I don't want to say bad words, so I don't say anything. Many companies introduce Scrum and they say that we introduced Agile, okay? And they don't really do Agile. So in Agile, the whole idea is that the part of the idea, actually even in Scrum, the idea is that the small units, the developers have a lot of power. But in many companies, what they actually do is introduce Scrum top down, and the management tells, okay, you have to be independent this way. And well, that's not what it's about. But well, so in many places, many people will complain about Agile or Scrum, but it's primarily because they were introduced in an incorrect way. So it's not a way. Kanban is another style, which is the idea is that you have some work that you have to do, and then you sort of make progress in all of them, and you somehow map them. DevOps is a move. Okay, so DevOps is another my heart aches. So DevOps was originally a movement where they said, okay, let's take the developers and the operations people to talk to each other, and the QA department, and make even work together. These days, if you hear the word DevOps, it's usually they think about people who do operations, and they also understand how the cloud works. Okay, but the DevOps movement is also sort of quite connected to this agile movement, basically, to make the software development practice better, easier, and give actually products to the client well. And XP stands for extreme programming. And that's the last thing. I really like actually what's behind extreme programming. The idea there is that there are certain things in programming that work well. Let's do it to the extreme. Okay, so for example, we figured out writing tests actually useful, so let's write always tests. Okay, and that's sort of the basic idea of extreme programming, and very few at the end, very few companies actually practiced it, unfortunately. But you see the results when you're trying to use some software or some web application or so, then you might encounter issues. Okay, so I talked way longer than I actually planned, but at least I hope that you also enjoyed it. I did. So
Definitely, yes.
So thank you for listening, and then we'll get back to some of the Python material later on. Okay?
Yeah.
Thank you. Bye-bye.
See you.